Oh, okay. So we are officially starting lesson 1.3, and that is domain and range. So you've actually done domain and range before in grade 10, but it was very specific to parabolas only. Now we're going to be looking at a wide range of functions and relations and looking at the domain and range of those. So to start, we need to go over our definitions of domain and range. So domain is the set of all values of the independent variable of a relation. In other words, what are all the values that x could take? Is x limited to any specific values? Is there anything x cannot be? That's what we want to state in our domain. Our range is the similar idea, but for our y's. So it's basically the set of all the values that our dependent variable can take. So what values can y have, in other words? So to state our domain and range of a function, we need to first review all of the symbols that we use to write this out. So when we write our domain and range, we're going to write a statement in math. It's kind of like writing in another language. So just as a reminder, we have our number systems. And the first are our natural numbers. So if you only have 1, 2, 3, no decimals, nothing in between, those are called our natural numbers. Next, we have our whole numbers. So that just includes 0. That's the only difference between our natural numbers and our whole numbers. Again, no decimals, just 0, 1, 2, 3. Next is our integers. So our integers include -1, 0, 1, 2. So it is negative numbers, positive numbers, and 0. And finally, we have all of our real numbers. So this includes all integers, all decimals in between. So instead of having individual points that count, we have everything in between. So I could have 1.5, I could have 1.0002. Everything in between is included in my real numbers. Now our inequality symbols. We did use these earlier today, and we hadn't reviewed them, so hopefully they weren't too confusing. The first one is our less than symbol here. And the way to think of it is that you want to think of it like a little alligator mouth, and the alligator is always eating the larger number. So that's the way to think of our inequality symbols. But that first one is our less than symbol. So our little example here is 2 is less than 3, and that's how you would say it. 2 is less than 3 in normal English. Next, greater than. So again, the opening of the little alligator mouth is on the larger number. And that one would be read as 5 is greater than 4. Then we have our less than or equal to or greater than or equal to. And that means that, for example, x is less than or equal to 4. So that means x can equal 4 or anything below that. So it could be 4, 3, 2, 1, all of those. Finally, is greater than or equal to. So x is greater than or equal to 6. So that means x could be 6, 7, 8, 9, but it also includes 6. Okay, so quick little recap on that stuff. Hopefully that's all review for you. And the next thing we want to talk about is how we write our domain and range. So we use what is called set notation. And set notation is basically just writing this out in math. The best way for me to describe it to you is almost like we're writing it out in a different language. So as if we were taking this and writing it out in French or Mandarin or Arabic or Afrikaans, whatever language you want, same idea. It's just we're writing it in math. So if we look here, the first line says x, and then this funny e thing and then R. How that is read in English is the set of all values belonging to the set of real numbers. So that funny E there means is an element of. It's telling you that X belongs in the real numbers. Then this next set below reads X is an element of real numbers. So X is an element of real numbers such that X is less than or equal to 0. That's how that translates to normal English, basically, instead of this weird math English that we have going on. So let's go through and actually do some examples because that might make things a little easier. So for example 1, we're going to state the domain and range of the following relation. The first thing we're going to do is we're just going to describe it in words in normal English. So if I look here, I'm going to start by looking at my value of my X coordinates. So my X coordinates live between here and here. So all of my X values are sandwiched between -2 and 4. So let's write that just as a normal English sentence. X coordinates are between -2 and 4. Now let's do the same thing for my Y's. So if I do this for my Y's are sandwiched in between 8 and they go as low as 0 down here. So we can write that my Y coordinates are between 0 and 8. So all I'm doing is just figuring out which numbers are stopping my Y's and my X's. So now let's write this as set notation. So let's start with our domain. And our domain is for our X's. So how we write this in our set notation is I write one of these funny Batman brackets, and we're going to say that X is an element of real numbers. So all of our numbers, X will always be an element of real numbers. And then I draw this funny R. That R means real numbers. Then the line means such that -2 is less than or equal to X, which is less than or equal to 4. So how we read that would be X is an element of real numbers such that -2 is less than or equal to X, which is less than or equal to 4. So basically, X is sandwiched in between -2 and 4. Let's try the range now. So for our range, we have that Y is also an element of real numbers, right? Because we have this nice curve. Y can be anything along within this interval that we're going to make. So we have that Y is an element of real numbers, and 0 is less than or equal to Y, which is less than or equal to 8. And then I close it with one of those funny brackets again. So that is our setup of our domain and range. If you can get a picture, so have the graph and just identify where my X's and Y's are sandwiched between, it makes figuring out the domain and range much simpler. Ethan, you can unmute, and then once Ethan's done, then we'll go to Keith. So Ethan, you can unmute and ask your question if you want to.
Are we only going to be working with real numbers and integers for the domain and range?
Yes. So everything that we have will have real numbers. And actually, we could have integers. Never mind. So we could have integers if we don't have them all connected in a line like that. So we'll get to some examples like that in a moment. But it'll primarily be R.
So we're not learning about working with like complex numbers and like.
No, no complex numbers in this course.
Okay.
Yeah, good question. Oh, okay, nice. That is in grade 12. You will have an opportunity to see it with complex numbers. So for right now, all those number systems that were at the top, that's all we'll be using. Okay, so let's do another example here. So for example 2, we have all of these dots. Now, it's important to note that they're not connected. So that means that we don't have these values in between the dots. We only have the dots. And all of my dots are on whole numbers. So we have on 0, 1, 1, 2, things like that. So if I go up and I reference all my number systems, because I have all whole numbers, so no decimals, and they are positive and negative, I am looking at my integers. So then I can write that my x is an element of integers. So it's not just an element of real numbers because there are no decimals, such that -3 is less than or equal to x, which is less than or equal to 3. So if I look where my x's are sandwiched between, they're sandwiched between +3 and -3. So that is how I write that domain. Now let's look at my y's. So my y's are sandwiched between 4 and -2. So similarly, my y's are also an element of integers. And the reason they're integers is because we don't have a line connecting all of them. It's just the whole number points. And it's sandwiched between -2, which is less than or equal to y, which is less than or equal to 4. Okay, let's try another example. Hopefully this one is fairly easy to follow because we did them last year in grade 10. So let's start by identifying where our x's are limited. So is there anywhere on this graph that's stopping my x's? If I look, I'm going to notice these 2 arrows here. This means that my graph goes on forever and ever and ever and ever and ever and ever on both sides. So this is just a snapshot of the graph, but the graph actually continues. So that means it's going to keep going out slowly and slowly forever. So there's nothing stopping my x's from growing. So that means that we can just say that x is an element of real numbers. And the reason this time it's an r instead of an I is because the curve is connected. So we have all of the values in between all the nice points as well. Now for my y's. I want to see if there's anywhere where my y's are limited. So if I look, my graph curves up, hits a turnaround point, and then comes back down. So my y's cannot go above this 3 here. So my y's, because this is connected, are also an element of real numbers. But in this case, all my y's have to be less than or equal to 3. So that is our setup for this one. I'm just going to quickly take one moment just to do attendance and just quickly take a picture of these just in case anybody has to go. I want to make sure we're all accounted for. Okay, there we go. All right, so continuing on. Oh, Alan, do you have a question? You can unmute or type it in the chat, whatever you're more comfortable with. Would it matter if the y or 3 came first on the range? So I'm assuming that you're talking about the one we just wrote. We want to have the y first. It's just proper form to do that. We could have 3 is less than or equal to y. It's technically not wrong, but writing it like this is proper form. So our options really are to have the y in the middle or the x in the middle, like this example, or we have y and then it on the right. The reason we do that is because it is how you would read it in English, basically. Does that make sense? Perfect. Okay, Jessica, so you're next. You can either unmute and speak, or you can type in the chat if you prefer. Y domain is X's element of real numbers. Sure, no problem. So there's nothing limiting our X's here. If we look on this example over here, my X's are sandwiched between -3 and 3. They can't expand any further than that. If I look at this one up here, my X's are sandwiched between -2 and 4. It can't go any further than that. Now, on this example over here, my X's actually go on forever. There's nothing limiting them or stopping. So in that equation, whatever the graph was, I could put in any X value there and it would work, basically. So because I have those little arrows on the end, it's just going to continue forever and ever and ever, and there's nothing stopping my X's. If I got a really big piece of paper and saw the rest of that graph, my X's would just keep going. Does that clear that up a little bit? Okay, amazing. All right, let's do another example. These ones have something a little different to them. So if I look at this example here now, we have a line, but we have kind of a funny dot here. So when I have a solid dot like this one here, this solid dot means that that point is included. This open dot over here means that that point is not included. It means that my line gets really, 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 really close to it, but never touches it. So that actual specific nice point is not included in our domain. So let's start by finding our endpoints for our X's. So my X's go from 1, 2, 3, 4, -4 over here, and are sandwiched between -4 and 3. The important thing to note here is that this 3 is an open circle. So that means that the actual number 3 is not included in our domain. So let's start writing out our statement. So we draw our funny little bracket, and then we say that X is an element of real numbers. And the reason we're using R is because all the dots are connected in a line. So all the decimals in between have to be accounted for. Next, we look at what X is sandwiched between. So we have that -4 is less than or equal to. And the reason we do less than or equal to is because it is also a part of our function, because it's a colored in dot. X, which is less than 3. So the reason why we have a less than 3 at the end is because it is a open circle, and the actual 3 is not included. Now let's take a look at the range. So my range is between 4 up here, and down here it's at -2. Now again, at -2, there is an open circle. So that number -2 is not included in our range. So again, we have that y as an element of real numbers. And again, we say real because it's connected with a nice line. And we have that -2 is less than y. And again, we use that less than instead of less than equal to because of our open circle. And that is less than or equal to +4, like that. Okay, let's try another one with some of these funny dots in it. So our next one here, we have a few different spaces here. So we need to be very careful when we're putting this together. So let's start by looking at our domain and figuring out where it's stuck between. So my x's are stuck between -5 over here. And if I notice, it is an open dot at -5. I'm just going to stop for 1 second and just answer Ethan's question really quick. You can unmute or type in the chat.
Can you explain again how the dots affect the domain and range?
Sure. We're going to have to explain it for this one, so it actually fits in really well.
Okay.
So this being an open dot means that that endpoint does not count in the domain. It means that my line goes towards my dot, but doesn't actually touch it. So that point is not included. So my domain goes towards 5, but -5, sorry, goes towards -5, but it never actually touches -5 is the idea. So it would be everything larger than -5, but it wouldn't actually include -5 itself.
So it would be x is an element of all real numbers, and x would be greater than or equal to -5, but it's not actually on -5.
So in that case, we would just say it's greater than -5 because it doesn't actually touch -5. So that's the difference between saying greater and equal to versus just greater than.
Okay, so just greater than 5, greater than -5.
Yeah, exactly. There you go.
Okay. All right, thank you.
No problem. Okay, so that's the first part, right? It's greater than -5. And my x is also sandwiched over here at +11. Kind of hard to see. Anything you would get on a test or a quiz or assignment would be very obvious where the points are. So if I look here on 5, I do have something funny going on as well. So x, we have this little jump here. So at 5, we have an open dot. So 5 isn't included there, but 5 is included up here. So what that means is that it ends up being a continuous line because we have these open and closed dots. So just be mindful of that. It's a little funny, but it keeps it being continuous. So because we have connected lines, x is going to be an element of real numbers. And now the one end point is 5, but it's an open 5. So 5 is less than x, so x is greater than 5, but it's less than or equal to, oops, sorry, that should say 11 because it's a little bit further. And now if I look at my y's, the y's are a little different here. My y's only have 2 values. So my y's are here at 6 and down here at 2. So I don't have really a range for my y's. I only have 2 specific values for my y's. So I can just write that out. That range is 2 and 6. I don't always have to have an interval for my domain and range. Sometimes my domain and range is just specific numbers, and that's okay. All right, let's do another example. So we're going to do some domain and range from equations. And these ones get a little tricky, but I find the easiest way to do it is to draw a little sketch. So we are going to have to back up and go back to some of our grade 9 and 10 knowledge to remember how to sketch these things. So the first one is y equals 3x minus 5. So if we remember from grade 9 and a little bit of grade 10, this represents the equation of a line. And that means we have our y-intercept at -5, and we have a positive slope. So we're going up like this. So this is just a little snapshot of our graph. It actually goes on forever and ever on either side. So if I'm going to write my domain and range, there is nothing at all that limits my x's. My x's can just keep on going forever and ever. So I say x is an element of real numbers. Now I look at my y's. So similarly, my y's have nothing limiting them either. So they just keep going on forever and ever and ever. So my y's are also an element of real numbers. So that's our first example doing it from the equation. The next one is going to be a parabola. So we're going to do a little bit of grade 10 review, and we will be reviewing all of these different functions in more detail later on. So for the moment, just bear with me if you're looking at this feeling like, oh, I don't remember how to graph parabolas. Please don't panic. We will be talking about it more later on. So the idea right now is just to understand where my x's and y's are limited. So here we have my parabola, and it's been moved up 6. So my vertex is at 0, 6. So this is 6 here, like that. And I also drew my arrows. So similar to my line, it keeps going on forever and ever and ever. So if I think about where my x's are limited, there's nothing limiting my x's. This is just a snapshot of my picture, but it actually continues on forever and ever. So because there's nothing limiting what my x's can be, I can just say that my x is an element of real numbers. Any number for x works. There's nothing stopping it. Now for my y's, if I look, there's no y's at the bottom half of my graph. All of my y's are above 6. And the arrows are pointing up. So it's just going to keep increasing above 6. So how we write that is that y is an element of real numbers such that y is greater than or equal to 6. Now we have a greater than or equal to here because y can equal 6, right? 6 is on the graph, so y can equal 6 and be anything bigger than that. So that is from an equation. We're almost done. This is a little bit long, but we're going to do the last one together. So a function represents the relationship between the height of a ball and the time elapsed since the ball was thrown. The ball reaches a maximum height of 20 meters after 1.5 seconds, and the ball hits the ground at 3 seconds. So what we need to do is state a reasonable domain and range for the relation. In order to get a better understanding of the situation, I'm going to start by drawing a little diagram. So here's my diagram. We have my height of the ball, and we have my time. So the best way to think of these kinds of diagrams is picture my time axis almost being like my, it's like I start a stopwatch. So you can kind of think of that as like the grass at the bottom. And so my ball shoots up from the ground. It's kicked, goes up in the air, and comes back down to the ground. And when it hits the ground, it's been 3 seconds. And it reaches a maximum height of 20 meters. And that happens at 1.5 seconds. The first thing we always do is we set up a picture, makes a world of difference. And now let's figure out where our X's and Y's are sandwiched between. So because this is a real life situation, our height cannot go lower than 0, and our time starts at 0. We can't go back in the negatives. We can't have negative time here before we kick the soccer ball. So our time is stuck there, and then we only care about our time until the ball reaches the ground, which is at 3. So our X's are sandwiched between 0 and 3. Next, because we've connected it in a nice line, this is in the real numbers. So for my domain, we can say that X is an element of real numbers such that 0 is less than or equal to X. And we say less than or equal to X because X can equal 0 and it's less than or equal to 3. So it's sandwiched in between 0 and 3, and it can equal those endpoints. Next is our range. So if I look where my range is between its max height of 20 and 0, which is the ground. So my ball can't go underground. Once it hits 0, it's sitting on the ground, so it can't go any further than that. So because the line is connected with a nice line, we say that Y is an element of real numbers such that 0 is less than or equal to Y, which is less than or equal to 20. And again, we're using less than or equal to signs because Y can equal 0 and it can also equal 20. Okay, and now for B, we're going to go back to lesson 1. And it says, is this a function? So what we're going to do is we're going to do our vertical line test that we were doing way back when. So I'm going to draw a vertical line, and I want you to picture it sweeping across the whole thing. At any point, is my orange line going to touch the curve twice? So because it won't, we can say this relation is a function because it passes the vertical line test. And that is our final answer. So that is everything for this lesson. If you are feeling like you need a little bit more practice, you are more than welcome to go in the textbook and look at the domain and range pages and take a look at that. So if you would like that, just let me know and I can send you that way. But our next thing that we have to do today is we just have one more lesson. So all of that can be found on Classroom. And that is supposed to happen during Block D at 2:15 to 3:33, but you're more than welcome to get a head start on it. Are there any final questions before we end this lesson meeting and I send you on your way to either work on our last lesson of the day or finish up other things? Yes, Tony, you can either unmute or type in the chat, whatever you prefer. range of the fourth question, example 2. Oh, I think you're talking about this one here. If you're not and I'm doing the wrong one, just let me know. So the range for this one is just 2 and 6. And the reason for that is because if I look at all my y values here, the only y values it has are 2 down here and 6. So all of the points on the bottom line have a y value of 2, and all of the points on the line that's on top have a y value of 6. So y isn't a part of any interval. Y just has 2 specific values that it can take. So how we write that is we simply just put that my range is 2 and 6. It kind of seems silly and different than all the other ones, but that's just how we write the range for that. Yeah, Dustin. If people feel comfortable with all of this and they are ready to start working on lesson 1.4, which is posted, you're more than welcome to leave the meeting and start working on other things. That's totally okay. And then I'm just going to stay here for a bit and answer questions. So if you need to leave and work on other things, that's totally okay. Just remember that we have our end of day Google Meet and attendance at 3:15. Okay, so Dustin's question, what if the domain and range is not equal to a number in between? I'm misunderstanding your question a little bit, I think. So I'm just going to ask for some clarification. So do you mean if it's not in a range? Is that your question? Or I'm trying to think of an example that might be what you're looking at. Maybe it's similar to this one, number 4 here, where it only has specific values. You can have that. Oh, I see what you're saying. Never mind. I think you're asking about a situation like this, so correct me if I'm wrong. So if I had a situation like this, where I have a line, but I have this one random point that it can't be, and this, and that one random point is at 1, 4. That's what you mean. Okay, awesome. So how I would write this is it's a line. So it is extending on forever. So my domain would be x is an element of real numbers such that, and the only thing that x can't be is x cannot be equal to 1. So you can write it like that. That's absolutely fine. You could also write it like this. X is an element of real numbers such that, and write out a long set of ranges. So we could say that x can be between infinity and 1, comma, the other end. But that's the easiest way to write it. But if you wrote it in a longer interval, that would be okay too. Similarly, for the range here, we would have y as an element of real numbers such that y cannot equal 4. So I think that's the situation that you are referring to. Would that be on a test quiz? No, because we haven't really covered it in the notes. So I wouldn't put that on a test or quiz just because we hadn't really explicitly done it in the notes. But it is a good thing to know just for the future. What if the domain and range is limited to? So I'm misunderstanding what you're asking. So if the domain and range is limited, That would be something like what you've written there could be something that looks like this. So we would have 5 and 10. And let's say I had a open circle here and an open circle here. I think that's what you're referring to, because it never really touches 5 and it never touches 10. It's just the stuff in between. Oh, and a circle in the middle. Okay. So let's say I have a circle in the middle like this. Then I would have to do it in these two chunks. So I'd have a chunk from here to here and another chunk from here to here. This is what we would call a piecewise function. So it's a function that's in two separate chunks. It still is a function, but it has two different chunks. So we won't really be covering this on our assessments, but it is an interesting thing to talk about. So what I would say for my domain is X is still an element of real numbers because it is connected in a line. So we still have an element of real numbers, but we kind of have two domain chunks. So we would have that, and let's say this dot was at, I don't know, 7. I'm just kind of making something up. So we would have 5 is less than X, which is less than 7. And then we would have 7 is less than X, which is less than 10. So you can write it like that, and you can just have different intervals separated by commas. That's totally okay too. I think that's the situation you were referring to. I suppose you can. Typically with a piecewise function, which is what this would be called, this would be the form that we would use. So we would use this because that is a standard thing that happens where I have like a chunk of a function over here that looks like this, and then it stops and continues here. So this is a pretty common thing that happens. So we usually go about writing it this way just to streamline it a little bit. So that's usually our system. If I were to include the can equal 7, then I would write it like this. 5 is less than X, which is less than 10. And instead of having a line there, I would have a comma. You could write that too. It's not wrong, but the proper form that we would use for a piecewise function is this up here. So it's not that it's incorrect by any means, right? Because if you're reading it, it really kind of says the same thing. But just for consistency, that's usually the one that we go with. No problem. Are there any other questions before we head out? There's a lesson 1.4 for you guys to be working on, and then some homework too. So if not, feel free to head out and start working, and then email me if you have any questions. I'll just wait until everybody goes in case there are any questions.